So today what we're studying is the counting principle. The first thing we're going to do is look at a visualization of it with a tree diagram. So our tree diagrams are used to display all the possible outcomes and gives us a way to count those possible outcomes. So in part B we have this example. The school cafeteria sells sandwiches, for which you can choose one item from each of the following categories. So to build our sandwich, the first thing we get to choose is our bread. Do we want white or wheat? So white or wheat. Then we get to choose what kind of meat, turkey or ham. So if we do white, we can do turkey or ham, and if we choose wheat, we can do turkey or ham. And we get two condiment choices, mayo or mustard. So if we did turkey, we could do mayo or mustard, mayo or mustard, mayo or mustard, mayo or mustard. And when we look at this, and we look at the end of the branches, we have 1, 2, 3, 4, 5, 6, 7, 8 different sandwiches that we could make, given 2 choices for bread, 2 choices for meat, and 2 choices for condiments. Okay, so do you see how to create the visualization with the tree diagram? All right, work together. Talk about this situation here about breakfast, and let's see if you can create a tree diagram. Go. Okay, so we're making our breakfast here, and we get to choose from 3 different entrees. So we either have pancakes, waffles, or eggs. And then we get to choose a drink. We either get orange juice or apple juice. Orange juice or apple juice. Orange juice or apple juice. And then we also get a side. So for a side, we can either get sausage, bacon, or ham. Sausage, bacon, or ham. Sausage. How many of you got frustrated at this point because there wasn't enough room? And you're writing really small. And this got really boring. And the same thing was happening over and over again. Anyone? Alright, yeah, me too. So here we have this great tree diagram where we can visualize all of our choices. And we had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 possible outcomes. But there's got to be a quicker way. Who can tell me what it is? What you got, Jason?
You multiply the choices for the different selections. So for like you have 3 choices for the entree, and then 2 for the drinks, and then 3 for the sides.
Bingo! And this is the counting principle. Okay? So if we had taken the total number of choices in each category and just multiplied them, 3 times 2 times 3, don't we get 18? And that is the counting principle. So it's a time saver, and it's a space saver, and it gives us the total possible outcomes. Now we can't see them specifically, so sometimes the tree diagrams are still handy, but it is a quicker way. So the counting principle says if there are m ways to make one choice and n ways to make a second choice, then there are m times n ways of making the first followed by the second. This is generally used when a tree diagram is too large to construct. So, in our first example, you get to choose a computer password. The password has 3 letters followed by 3 digits, but they give us some restrictions here. And question 1, it says how many passwords are possible if the letters must be uppercase? Okay, so if we're only looking at uppercase, that limits us a little bit, but we know we need 3 letters, first letter, second letter, third letter, followed by 3 digits. First digit, second digit, and third digit. Alright, so if my letters are restricted to uppercase only, how many possible choices are there? 26. Did it say anything about can I repeat or not repeat? It didn't, so I get to repeat. 26 and 26. Now I'm switching to digits. So when we talk about digits, we're talking about the numbers 0 to 9. So how many numbers are there 0 to 9? 10. And since it doesn't give me any restriction, it's 10 times 10 times 10 times 10. Okay, so we multiply these out, and we get 17,576,000 possible passwords. Okay, now the second case did give us a restriction. How many passwords are possible if no letter or digit can be repeated, and the letters this time have to be lowercase? Well, if we're restricted to lowercase, we're still at 26. If they didn't restrict us, we'd have how many possible letter choices? 52. We just double that. All right, but this time we can't repeat. So for the first letter, I have 26 choices, but for that second letter, what do I have now? 25, and then 24. And now with my digits, for my first digit, 10, but for my second one, and then my third one. All right. So 26 times 25 times 24 times 10 times 9 times 8. We are down to 11,232,000 possible passwords. So what we have determined using the counting principle is what does our total sample space look like? Okay, and we're going to use this when we do probability, because probability is always the favorable over the total, and the counting principle gives us the total. Okay, you try with the people around you to see if you can figure out part B, 1, 2, and 3. that's really good for the first time you've used a movie.
Thank you.
You're welcome. You got it, Tom? Alright, so when there are no restrictions, Joseph says that for 4 digits we have 10 times 10 times 10 times 10, which is 10,000, and he's absolutely correct. Do you guys agree? Yeah? Alright, so number 2. This time we do have a restriction. It says the first digit cannot be a 0 or a 9. Alright, so what do you think? That's right. That gives us 8 possible choices for the first digit. So does anything else change? No. Alright, so we have 8 times 10 times 10 times 10, and that gives us a total of 8,000. Awesome. Okay, who's got the last one? I do. Alright, so the last one. The first digit can only be a 1. So how many choices do we have? 1. And so that leaves us with a total of 1,000. Alright, any questions about the counting principle? Okay, that second sheet that you picked up that has front and back, some of these are really fast. Don't be scared if you think they're easy. Some of them are easy. Okay?